In this video, we'll see one example of SFD and BMD. So here we have this beam which is supported at 2 points, A point and C point. Here it's a fixed support, here is a roller support. Now there is this varying load from A to C, which is 60 Newton meter at the highest point at C. There is one moment, pure moment acting 5000 Newton meter at the B point. This is 3 meter. B to C is also 3, C to D is 5 meter. At D there is a point load of 600 Newton. Now first step, we have to find the reaction forces at support RA and RC. So first equilibrium equation, summation of Fy equal to 0, we'll get Ra plus Rc equal to this triangular force downward and this point load. So this triangular force will be, varying load will be this area. So area will be 6 meter into 60 divided by 2 because it's a triangle, so half into base into height, so this plus 600. So this total downward force will be equal to upward force, which is Ra and Rc. Now summation of moment at A equal to 0. So if you see, first we have to calculate moment for this triangular area. So this varying load, we have to calculate moment, and this, if we take its equivalent force, then it will be acting at 2 by 3 distance from this 0 force. So from here to here, 2 by 3 distance will be 6 into 2 divided by 3. So that will be the distance, and the total force which we have calculated, which is area, so half into base into height. So this force will be assumed to be concentrated at 2 by 3 distance, and that will give us the same result as this load. So 2 by 3 of 6 meters, so somewhere here, and the value of load is this much. Now 600 into total 11 meters. There is one pure moment which is opposite to both these forces. So if we are taking this positive, then that other force will be in negative direction, which is minus 5000. And RC is also in the same direction as this 5000 counterclockwise. So that will be minus 6 RC, but on equal to side, on other side of this equal to sign, we have to consider positive. So if we take minus 6 RC, that will be equal to 0. So summation of all forces will be equal to 0. So RC is at 6 meter. So minus 5000 and minus 6 RC are on the same counterclockwise direction. So this equation and this equation combine, if we combine here, from here if you find RC, that magnitude will be this much, and after calculating RC, if we keep in this equation 780 Newton, then we get Ra. So now we have both Ra and RC. So second step will be finding the shear force. So finding shear force, first we have to calculate from this point. So here we know that the reaction force is that 393.33, which is Ra. So we have shear force Ra. Now there is this Ra is upward direction. Now this varying load is coming, and it is continuously increasing its magnitude, and it is in negative direction downward. So Vb minus Va, if we calculate, then it will be this much area from A to B triangular region. So that will be equal to minus half into base into height. So half into 3 into height will be, here it is 60, so halfway it will be 30. So here it will be 30 Newton meter. So that will be the Vb minus Va. So Vb minus Va will be equal to area. That if you want to understand how it is how it is coming as an area of this triangle, go to previous video. I have explained that dv by dx is equal to load. So we will be equal to integration w dx. So integration of w dx means the area of the load with respect to distance. So now if we keep Va value here, we get Vb, and to calculate VC shear force. Again we can calculate VC minus VA equal to this area. So VC minus VA equal to minus half 6, or you can, or one method is there that you can directly calculate all the forces and add it. So if you want to calculate a shear force at this location or somewhere here, then either calculate all the forces on left side or the right side and use the sign convention which we have discussed. So that way you can also calculate. So I am choosing to go with this area method because there is no need to remember the sign convention here. So VC minus VA equal to minus half into base into height. If we give VA value here, we get VC. Now VC dash is there because there is one reaction force, sudden change in shear force. So VC dash will be equal to this VC plus the reaction force because both are positive. Here if you see RA, we are taking positive direction, upward is positive, downward is negative. So total will be 600 Newton, and at D point it will be 0 because this VC dash 600 and VD, that will be minus 600. So shear force after coming to D point, that will again comes to 0, so that is in minus direction. So again at a D point it will come to 0. But if it is asked in question what is a shear force, then we have to tell entire magnitude, which is equal to 600. Its magnitude, if you see at a D point, the shear force magnitude is positive, but if we are coming till here, it will end at 0 point. So if it is asked in question what is the shear force at D point, we have to calculate it positive 600 because it's on positive direction. Now if you want to plot this, then you see this uniformly varying load, it's linear, so here it should be parabolic. So after putting the reaction, we have to come down, and first we have to plot all these points, and then we have to connect with these lines. So first line is having negative slope because the load is in negative direction downward. So negative slopes, all at all points the slope is in negative direction like this. Each and every point slope is in negative direction, and its magnitude is increasing, load magnitude is increasing, so slope value should increase. So from here almost zero slope, its slope is increasing in negative direction. Then RC is coming, so sudden change, so RC is 600, sudden 600 change, and then there is no load, so the slope will be constant, and again there is 600 Newton which is coming down at D point. So this is how shear force diagram will be plotted. Now the final step is finding bending moment. So here we know that at A point there is no bending moment, then because it's a pin support, simply supported, so there is no bending moment. Now at B point, if we take bending moment here at B point, so RA into 3 meter, and this half into base into height, half into 3 meter into 30 at distance of 1 by 3 from the B point, so 1 by 3 into 3. So RA into 3 minus half into base into height, and distance is 1 by 3 of 3 because B is on bigger side, so its concentration of this force will act at 1 by 3 distance from B point, 1 by 3 of this length 0 to 30. So this will come out as this much, 1135 Newton meter. So MB dash is here, we have to consider because there is a other pure moment is acting 5000. So at B point only, this 1135 plus it is in counterclockwise direction at B point. At B point, if we see, it is giving a hogging moment. If it is upward, it will give the beam a sagging moment. Here it is a hogging action. And if you see, this 1135 is acting in clockwise direction because RA we have considered positive and we got 1135. So it is in clockwise direction. This 5000 is in opposite direction. So the total at B dash point will be coming out as minus 3865. Now at C point, if we consider, then we have to consider RA, this triangle, and this 5000. So these three things we have to consider, or we can calculate from this side. So 600 into 5, that will be the moment at C, that we can say directly, because there is no other force involved. 605 is 3000, and it is giving a hogging moment. 600 is giving a hogging direction. So MC will be minus 3000. So if we plot this, then from A point to B point, we have linear, so this will be parabolic and this will be cubic. And if you see shear force, value is decreasing, so slope should be decreasing. So here if you see, slope is decreasing from maximum slope to the zero slope, so it is decreasing, and bending moment is positive at B point 1135. So this is the curve, this will be cubic. Now there is minus 5000 sudden change, so 1135 minus 5000 will be minus 3865. Now at D point we know the moment will be 0 because it's a free end, and we know at C point this is minus 3000. So both this point we know, but we don't know this curve. So this curve is again the same cubic curve because entire curve is parabolic. This entire curve is linear from A to C. This entire curve is parabolic from A to C. So from A to C, entire curve should be cubic. Just 1 minus 5000 Newton meter is acting at B point, that's why this is breaking, otherwise it should be continuing till the C point. So these both curves are continuous and it is separated by this minus 5000. This is a linear curve because slope is constant, so here the bending moment slope is constant. Slope is constant means shear force is a slope of bending moment diagram. So shear force is constant, bending moment diagram slope will be constant. So this is how we have to plot shear force diagram and bending moment diagram. And two important points are, wherever the shear force is 0, bending moment will be maximum. In this diagram there is no where shear force is 0, so we can get bending moment at any random point maximum. So here we are getting, but wherever the shear force will be 0, the bending moment will have maximum value, and bending moment equal to 0. Wherever we get a value of bending moment 0, at that point is called as point of contraflexion. Here bending moment is not 0. At B point there is two bending moment acting, positive 1135, and on other side it is minus 3865 Newton meter. So here it is not 0, but wherever the bending moment is 0, that point is called as point of contraflexion. And this is the point where hogging and sagging are changing. Means if beam is in hogging, then it will start sagging, and if it is sagging, then it will start hogging. So this was the example for shear force and bending moment diagram. And thank you for watching this video, and see you in the next video.